Welcome to the MassStat Colloquium, our online colloquia for fall 2021. It is my great pleasure today to introduce our speaker, Stefano Costanzi. Stefano is a professor of chemistry at AU with an educational background in both chemical science and international affairs. His scholarly work is based on two main research lines. The first one revolves around the application and development of computational chemistry strategies to study the interaction between chemicals and living organisms. The second one revolves around the analysis of gaps in current policies and practices that allow for the proliferation of chemical weapons and the conceptualization of solutions and tools to narrow them. I've seen Stefano give a similar talk to, for example, the neuroscience group, and it was extremely well received. But on a personal note, I like to say Stefano is truly a friend of our department. He knows many of us through his interactions with the AU Senate. I know Stefano because anytime I get a chance at our wonderful broader STEM meetings, I sit down with the chemists, I sit down with the physicists, I sit down with the folks in psych, and I sit down, of course, with the people in computer science because I'm an affiliate of that department. And I think one of the great resources at American University is our STEM teaching. And I think that we really need to do as much or even more of these events where we work together collectively because the sciences at AU are spectacular. With that, I'll turn it over to Stefano, who's going to give us a talk on supporting the fight against proliferation of chemical weapons through cheminformatics. With that, Stefano.
All right, let me see if I can share the screen.
Yes.
All right, so here we are.
Excellent.
So the research that I'm going to present today, this is a talk that I gave this summer at a virtual conference of the IUPAC, virtual because of COVID, otherwise it would have been in Canada. And I hope that they're going to invite me again next summer because it's going to be in Calgary in person, hopefully, COVID allowing, of course. And the talk is related to the one that Steve mentioned before, the one that I gave for the neuroscience group, except that at that time we had conceptualized this cheminformatics tool. And now what I'm going to show you is that we have developed a prototype of this tool, which we are now ready to get tested, to get field tested by some select jurisdictions. So before I get started, first of all, I want to thank the Math and Stat department for the invitation, and it's always a pleasure to be here. I was invited, I remember, by Steve a couple of years ago, when I gave a talk on G protein kappa receptors, which is the other line of my research, the more pharmaceutically based research. Now this year, I'm going to talk to you about my research on chemical weapons. So this is research that I'm doing in collaboration with the Stimson Center, which is a think tank in Washington, D.C. Rick Cupid is the lead of the Stimson team, and there is also a colleague from George Mason University, Greg Koblenz, involved. And as a matter of fact, this line of work started from a conversation that I had with Greg here at the Davenport Cafe. Actually, we met, we had a coffee together, and we started to think about gaps that there are in policies. As Steve mentioned before, that's one of the things that I'm looking for, where these gaps are in chemical security policies and how they can be filled. And so from this conversation, it became apparent that the way that frontline officers check whether or not a like export control officers or customs officers, the way that they check whether or not a chemical under scrutiny, the chemical that they see being shipped, is part of a control list, is a bit problematic, as I will show you. So the Stimson Center, Greg from George Mason University, and then my research team here at American University with Charlotte Slavik, that has been working with me on this project since 2019, and Joyce Abides, who joined us more recently. And this is all sponsored by Global Affairs Canada, which is the Canadian equivalent of our Department of State. And of course, we're very grateful to Global Affairs Canada for sponsoring this, this research and making it possible. So let me give you a bit of an introduction on chemical weapons. Here, there is Jim in the audience that knows a lot about chemical weapons. Chemical weapons are weapons that are intended to cause death or incapacitation through the toxic properties of chemicals. So here we're talking about toxic chemicals, chemicals that are toxic specifically for humans and for animals. That's the definition of chemical weapons that comes from Article 2 of the Chemical Weapons Convention. The Chemical Weapons Convention is the treaty, the international treaty that bans, that poses an entire ban on chemical weapons. Not just on the use of chemical weapons, but a complete ban on chemical weapons. There is nothing that you can do with them. You cannot develop them, you cannot research them, you cannot stockpile them. There is nothing that you can do with chemical weapons. You can only research them for defensive purposes, for chemical defense. So those are chemical weapons, again, toxic chemicals, weapons based on toxic chemicals, and the toxic chemicals on which these weapons are based, we also call them chemical warfare agents. Most of us, when we think of chemical weapons, will think of World War I, rightfully, because World War I, of course, was a war which saw a prominent use of chemical weapons on a massive industrial scale, with over 200,000 of people that actually died as a consequence of the deployment of chemical weapons. Chiefly the chemical weapons that were used during World War I were choking agents like chlorine, for example, as well as vesicants like mustards or leucides. Leucides weren't used, in fact, they were developed though during that time, as a matter of fact, here at American University. However, chemical weapons is not just World War I. In the sense that chemical weapons are still very much used today. In a different way though, while before they were used, again, on a large scale, on a very large scale for state-on-state wars, these days they're used a bit differently. Specifically, they're mostly used for counterinsurgency purposes, for example, by regimes who are using these chemical weapons against civilian population. They're also being used for targeted assassination, so on a very small scale for targeted assassination. We have all seen what has happened in Syria, in the Syrian civil war. Chemical weapons have also been used in Iraq by non-state actors. Chemical weapons for assassinations. If you follow the news, in 2017, Kim Jong-nam, the half-brother of Kim Jong-un, North Korea's dictator, was assassinated with VX. After that, in 2018, Sergei Skripal, a former GRU official, a Russian military secret service member who had defected to the West, was poisoned together with his daughter with a Novichok agent in Salisbury, the UK. These Novichok agents are nerve agents that were developed in the Soviet Union during the Cold War. He didn't die, his daughter didn't die either. However, tragically, a couple of months afterwards, a local couple found a perfume bottle. It wasn't a perfume bottle, in fact. It was a bottle that looked like a perfume bottle, but it contained the same agent that had been used to poison the Skripals, and the woman died. She sprayed herself with what she thought was perfume, and she gave herself a massive dose instead of a nerve agent, and could not be rescued. And more recently, in August of 2020, a different Novichok agent was used for the attempted assassination of Navalny, Alexei Navalny, who is a political dissident, a Putin opponent, and he also survived the poisoning after being treated in Berlin. So very much of a current problem. And by the way, the fact that the chemical weapons landscape has changed from a situation in which chemicals were used on a massive scales to a situation in which chemicals instead are used for the same purposes, but on a smaller scale, made the whole issue of controlling chemicals much more complex, because it means that even smaller quantities of chemicals need to be controlled at this point. So how are these chemical controls? Well, let's say that at the international level, there are several frameworks that contribute to these controls. The main one is the one that I mentioned before, the Chemical Weapons Convention. And the Chemical Weapons Convention is a disarmament treaty. It's not an arms control treaty, it's a disarmament treaty, because it seeks to eliminate entirely chemical weapons, unlike other treaties that seek to control instead certain kind of weapons. And all of these frameworks, in order to work, they have embedded in them some lists of chemicals that are chemicals of security concern. So for instance, the Chemical Weapons Conventions has 3 schedules of chemicals in it: Schedule 1, Schedule 2, and Schedule 3. Here there is a 2 that is missing on the slide. And what are the schedules? These are chemicals that are recognized as being relevant as chemical warfare agents or precursors for their synthesis. They are not a comprehensive list of chemical warfare agents or precursors. In fact, the Chemical Weapons Conventions has the so-called general purpose criterion of the Chemical Weapons Convention, also through Article 2 of the Convention, establishes that any toxic chemical, no matter which, any toxic chemical that is used on purpose against humans or animals is to be considered a chemical weapon, irrespective of whether or not these chemicals are listed in the schedules. So what are the schedules for? The schedules are to support the declaration requirements and verification regime, meaning countries, state parties to the Chemical Weapons Convention, annually need to declare what kind of chemicals they have that are pertinent to the convention. And then this triggers a verification. So this is a particularly strong treaty. It has a verification regime whereby these declarations are verified by the Organization for the Prohibition of Chemical Weapons, which is the organization that supports the implementation of the Chemical Weapons Convention. And the reason why there are 3 schedules is because chemicals are dual-use items, as you know. Dual-use means that they can have at the same time a peaceful, legitimate purpose and a military purpose. Those that are in Schedule 1 are considered chemicals that have exclusively or almost exclusively a military purpose because of their high toxicity. For example, nerve agents are in them. In Schedule 2 and Schedule 3, we have chemicals that are more and more dual-use chemicals, where in Schedule 2, for instance, we have chemicals that are used also for pharmaceutical applications. And Schedule 3, instead, we have chemicals that are also used in very large quantities for industrial applications. So that's the reason for having 3 different schedules. And of course, there are different thresholds for the declarations that are required for the three schedules. But essentially, for Schedule 1, only very little quantities of the chemicals can be held by the state, but the state members, and only for chemical defense purposes. Conversely, for Schedule 2 and Schedule 3 chemicals, those can also be held by chemical industry for their legitimate purposes. And the other frameworks also have, and I'll talk a little bit more about the other frameworks that we're considering now. They also have their own lists of control chemicals. So let's take a look at this list just to have an idea of what this list look like. And here, what I'm showing you is a little bit of Schedule 1, the Chemical Weapons Convention, the CWC Schedule 1. Just the first few entries. One thing that I can show you over here, let me see if I can get a pointer, is that for some of the entries, for example, this one over here, or this one over here, these are individual chemicals that are identified through a chemical name, as well as a chemical abstract service registry numbers. For those who are not familiar with CAS registry numbers, these are registry numbers that are assigned by the Chemical Abstract Service Division of the American Chemical Society to a chemical whenever a chemical is disclosed. So these are numbers that have nothing to do with the structure of the chemical. They're just progressive numbers that are assigned to a given chemical. It's like a license plate, essentially, assigned to a chemical. So some entries are like this. Again, chemical names and CAS registry numbers. All individually listed chemicals are like this. But then there are other entries like this one over here, which instead are not an individual chemical. This is a family of chemical, family of chemical that is identified by a central scaffold with variable pieces attached to it. And this can be very large families. Like this one that we are looking at over here, which is the family of nerve agents to which sarin and soman belong. Those two are listed as example, but this family of nerve agents, if one enumerates it, depending on how one interprets these variable groups, this can encompass as many as 126,000 compounds. And there are certain families that are so large that they cannot even be enumerated. So clearly, this is a situation that is extremely difficult to interpret by people who don't have a significant training in chemistry. And typically, export control officers, customs officials don't have that. So for someone who does not have that type of training, looking at a chemical under scrutiny and trying to figure out whether or not that falls within the scope of a family, it's really not feasible. This was actually the initial impulse that gave me the idea that something had to be done in order to automate the system. So let me give you an example here. What we're trying to do, well, I'll give you several examples. I can actually, if there is time, I'll show you the actual tool in action. What we're trying to do, we are trying to help frontline officers to answer questions along those lines. They're given a name, they're given a CAS registry number. What do they do now? Well, what they do they try to match what they're given with what's in the list. If that's in the list, then that's a control chemical. If it's not in the list, then that's not a control chemical. Well, as I will show you, it's much more complex than that, much more complex than that. In particular, there are two main problems. The first one I already told you is the problem posed by the families of chemicals. Those are extremely difficult to interpret for, impossible, I would say, to interpret for non-chemists. So there is no way that a non-chemist, given a chemical name, will be able to match that with one of the families of chemicals listed in one of these control lists. The second problem affects individually listed chemicals. Those are easier to control, but not very easy. Why? Well, first of all, because the same chemical can be called with many different synonyms. And so the fact that a chemical name of the chemical under scrutiny is different from those that are in the list doesn't exclude in and of itself that the chemical is not one of those control chemicals. It may be just that the officer is looking at a synonym of one of the control chemicals. And plus, there is the issue that chemical variants, so different variants of the same chemical, for example, an isotopically labeled version of a chemical will have a different CAS registry number from the non-labeled chemical. So even there, looking at CAS registry numbers, although it's a bit easier than looking at names, is also not something that is going to give you a comprehensive answer as to whether or not the chemical is a control chemical. And so then the solution that we are working on, and this prototype that we have developed, is a cheminformatics tool. Cheminformatics is a discipline that is across information technology and chemistry. So handling chemical information with computers, essentially. And so what we are proposing essentially is a database management system with a database of controlled chemicals that through which export control officers can automatically assess whether or not a chemical under scrutiny is one of the controlled chemicals. And so very schematically, the system works the following way. A user can input the chemical in a variety of different ways, including the CAS registry number, the name that they're given, but also a structural identifier. I will talk about structural identifiers in a second, for those who are not familiar with those. The operator, if they know how to do that, can also draw the structure of the chemical into the system. And here the key is that no matter the way in which the chemical is entered, the chemical will always be converted into a structure. We are shifting the focus here from names and registry number to structures, and that's what makes this automation possible. Once the chemical has been converted into structure, the query chemical is standardized. So all those variants that I mentioned before are reconducted to a standard version of the chemical. So if you have inputted an isotopically labeled version of the chemical, that gets standardized into a canonical version of the chemical, non-labeled version of the chemical. The database is also standardized, so all the structures in the database are standardized. And therefore, at that point, the system is able to match the standardized query with the standardized database, pulling out all of the entries in the database that match the query, if any, of course. And to implement this prototype, we have used a commercial database, chemical database management system, which is called Instant JChem. This is a database management system developed by Chemaxon. And we have implemented a database that encompasses CW control lists from a number of frameworks in it. In particular, we have added to the database the 3 CWC schedules that I mentioned before. We have added the chemical weapons precursors list from the Australia group. The Australia group is an informal arrangement of 43 countries, actually 42 plus the European Union, that looks at harmonizing export controls, especially for precursors of chemical weapons, as well as for biological agents. The Wassenaar arrangement. The Wassenaar arrangement is a framework that is intended to control the transfer of weapons in general, and in munitions list 7, among other things, it lists chemical weapons and precursors. We then implemented a list, a Syria-specific list, which also stems from the Australia group and that has been implemented by a variety of jurisdictions, including the European Union. And the reason for this list is that, as you know, Syria is a particularly concerning state for what regards chemical weapons. And so chemicals that are not otherwise not controlled or not considered to be of particular concern are controlled with respect to Syria. And then going beyond chemical weapons, we have implemented a larger list of strategic chemicals implemented by the World Customs Organization, or WCO. And this list, again, beyond just chemicals of CW concern or chemical weapons concern, this is also chemicals of nuclear concern, missile, explosive, and more generally speaking, military concern. So 5 lists from 5 different frameworks. Okay, so let me show you then a bit the issues over here and how we are solving them. Beginning with the families of chemicals, and I'll try to give you a practical example if the computer assists me. It was giving me some problem earlier today, but hopefully it will work. Let's begin with the problem of the families of chemicals, and I'll give you an example. This chemical over here, this chloroethylamine over here, this is a precursor for the synthesis of the nerve agent VX. It is not listed explicitly by the Chemical Weapons Convention, but it is covered by one of the entries of the Chemical Weapons Convention that is a family entry. The entry, if one, this is the text of the entry, if one looks at it from the structural perspective, is like this. It has this central scaffold and 2 variable groups over here. So then the question is, given the text of this entry, right, of this family of 2B10, Schedule 2 entry, Part B, entry 10 of the Chemical Weapons Convention, how is an export control officer, just by looking at the name or the cash registry number, going to be able to match this, either the name or the cash registry number, with this text over here? As you can understand, it's not a straightforward task, right? However, with the tool that we are proposing, this can be done in an automated fashion. Let me see if I can stop the PowerPoint presentation here and show you how this is done with the tool. So let's say, for example, that I want to use the name, and the same thing can be done with the cash registry number. if one here, I'll just copy the name. And then okay, let me open the search. So here I can just at this point input the name into the system. All right, it's not taking it for some reason. Let me try again. Okay, here's the name. Then import. And the software here, this instant JChem software, will convert the chemical name into a structure. I could have done the same with the CAS registry number as well. Then I can set this as the query. There are a couple of things that need to be set, a couple of options that need to be set before running the search. And then at this point, I can just run it. And in a few seconds, I will get my answers. And so as you can see, I have several hits, one of which is from CWC Schedule 2. And then when I go over here and click on the hit, I will have CWC 2B10. So then I know at this point that this chemical is certainly covered by this particular entry, and it is also covered by the Australia group as an individual chemical, as well as by the World Customs Organization list of strategic chemicals, also as an individual chemical. So this is what the tool can do for families of chemicals. And similarly, the tool addresses also the issue of synonyms and chemical variants. And I'll give you another example over here. This is another precursor that we're looking at. This is a pinacolyl alcohol, which is a precursor for the synthesis of the nerve agent soman. And let me get the pointer. Yeah, this is the alcohol, and this is the nerve agent. So this is controlled by the Australia group, and the Australia group lists it as a pinacolyl alcohol. As you can see, this is the name in the list. And this is the CAS registry number that is given in the list. Well, for the name, you can call it pinacolyl alcohol, but you can also call it with many other different names. I just listed a few over here by way of example. Right, so clearly here, just looking for pinacolyl alcohol alone is not sufficient to exclude that this is not controlled. If you're looking for pinacolyl alcohol, you're going to find a match with the name, but if you're looking for one of these other names, you're not going to find a match, although it's the same, exactly the same chemical. This situation is partially addressed by the fact that all of these synonyms will have the same CAS registry number. So if you use the same CAS registry number, you are going to capture all these synonyms, which is good. And in fact, export control officers are trained to rely more on CAS registry numbers than on names, rightfully. That's the right thing to do. However, look at this. If you have this is the CAS registry number in the list, but if you're looking at different versions, different variants of the same chemical, and I just listed a few over here, like 2 stereoisomers, for example, one isotopically labeled version of the same chemical, but also this, which is just a different protonation state. So essentially, this is exactly the same chemical looked at a different pH. they all have different cache registry numbers. All right. So looking for exclusively for this cache registry number, that does not exclude that the chemical under scrutiny is not a control chemical, right? For instance, if you have this cache registry number, which is different from the one listed by the Australia group, or this name, which is listed from the one, which is different from the one listed by the Australia group, how you're going to be able to assess whether or not the chemical is controlled. If you just try to match names or cache registry number, you will conclude that the chemical is not controlled. And instead, and I'll give you another example, just like before, if I, in this case, I'll try with the cache registry number. So if I copy the cache registry number and I put it into the system, here's the cache registry number. We're going to import it. Here is the chemical on the screen. Different variant, but it gets standardized into the one that we want. We run the search. And even here, we will find that that is covered by several lists, including CWC Schedule 2, including the Australia group over here, which is the entry that we were using as an example, the list that we were using as an example, as well as the WCO list of strategic chemicals. Okay. We have also identified, while doing some internal tests, that the system has some limits. It's a prototype, and so of course it will have limits that will have to be addressed as this evolves into a mature product. And we're looking forward to identifying more limits as we go ahead and test the system on the field, again, with a couple of select jurisdictions, which we intend to do in 2022. The main issue is that, not the main issue, but one of the issues is that the interface is really an interface that targets chemists or people that are familiar with this sort of cheminformatics tools. It's not necessarily an interface which is the most straightforward interface to use for the general public. Also because the system is intended to manage, create, and then query databases. So it has all the functionalities that are needed for to perform these tasks. So one of the things that we want to address going forward is to come up with a system that is more streamlined, that has only the functions that are needed for the operators, so that it's less distracting and easier to use. And also, while right now, as you've seen, we are working with a desktop-based tool, we want to transition to a web-based tool. And this is also due to feedback that we got from a number of stakeholders, many of whom have issues with installing third-party softwares because of the mandates of their agencies. And so having something that resides on the web has some advantages there. So that's one issue that we are seeking to address. The other one is relates to the fact that although I have shown you that you can put in names or registry numbers and those will be converted into structures, in fact, that doesn't always happen. For cache registry numbers, it happens most of the times, but there are situations in which some cache registry numbers cannot be converted into structure by this system. As I mentioned before, cash registry numbers are numbers that are not, they are nothing in them that pertains to the structure of the chemicals. So a computer, given the number, cannot reconstruct the structure unless it has a connection to a database that connects the numbers with the structures, a relational database that has that connection. In the absence of that, the conversion doesn't happen. So you need a very comprehensive one. The good thing is that, however, it is always possible to input chemicals in a different way, specifically by using structural identifiers. So for instance, if you're looking at this chemical over here, this is an isotopically labeled version of serine, where the phosphorus is a less common phosphorus isotope. So Instant JChem will not take the name nor the cash registry numbers. It will not convert them into a structure. However, structural identifiers can be used, and structural identifiers are strings that codify entirely the structure. So they have all the information in them that the computer can use to algorithmically reconstruct the structure. These are two of the most common structural identifiers: SMILES and INCHI codes. INCHI codes were developed by IUPAC, while SMILES have been in use for many years and were developed by cheminformatics industry. SMILES are really the gold standard for a variety of reasons when it comes to cheminformatics and structural identifiers. And so, as I can show you over here, if you have, if you take this cash registry number, no cash registry number, sorry, this SMILES identifier, and you put it into the system, this is converted into a structure. Look, a labeled structure, which however gets standardized, so it doesn't matter anymore if it's labeled, and it's matched against a standardized database. So we pull out serine, just as we wanted to. So here, beyond the fact that certainly we are looking forward to, in future versions of the tool, we're looking forward to have a more robust engine for the conversion of cash registry numbers to structures, but we're also seeing an opportunity for an important policy change where whoever ships chemicals, beyond being required to provide a name and a cash registry number, is also required to provide a structural identifier, which in conjunction with this type of tools would significantly bolster the ability of export control officers, frontline officers in general, to control chemicals. And this goes also not only in favor of chemical security, but it is also extremely advantageous for chemical industry, because if the controls are quick, then it means that all legitimate transfers can occur rapidly without being hindered by controls. And so with this tool, again, the ultimate goal is to, on one hand, stop the illegal transfers of chemical warfare agents and precursors, or chemicals of security concerns in general, but also allowing, facilitate, in fact, the transfer of chemicals for legitimate purposes. And I'll stop right here. Again, thank you all for your attention, for the invitation, and above all, I want to thank again Global Affairs Canada for the financial support, which has really been fundamental for us to conduct this type of work. Thank you.
Well, thank you, Stefano. I think the first thing we should do is thank Stefano for a spectacular talk. I mean, I think that was just
Thank you.
well put together, and I especially enjoyed the live demo of your software and its impressive software. Um, we now have time for questions. I'll open the floor up. So, does anyone have any questions? Well, I guess I'll. Okay, John.
Well, it just seems that this is a great step, but it still seems like you need somebody quite knowledgeable at the front end. Is there any hope of having some kind of sensor, maybe a mass spectrometer or something, that could sample and feed into the system? Or
Okay, let me your question is essentially divided into two parts. Indeed, it's complex. In fact, right now we are engaging reachback centers and jurisdictions that do have reachback centers. These reachback centers are centers where there is someone who has more expertise than the frontline officer would have, so that the frontline officers, when presented with a case, which is not a straightforward case, so essentially a name that does not match whatever is in the list, gets to the reachback center. The reachback centers uses the tool, gives them an answer. Your second part of the question, that becomes extremely relevant if one wants to control what does not get declared, because clearly with this we control what's get declared, right? I mean, if an exporter is exporting sarin, but in fact is declaring that it's exporting something else, there's nothing you can do with this tool. Coupling it with a sensor system as the one that you were suggesting would address an issue like that as well.
Yeah, agreed. So I have a follow-up question to John. Actually, that was one of my questions. I think your system is brilliant, because what it's doing is it's taking all this information and putting it in one tool, so that if there is a systematic analysis of the chemical, there's at least an opportunity for people to understand, oh, this is, maybe it's not sarin, but it's a pre-ingredient for sarin. So you could catch somebody gathering chemicals to make a more potent chemical. But the second thing is, to John's question, is the bad actors. So the bad actors are going to be the really hard situation, because they're not going to report things,
right,
or they're going to try to hide things, and how one could deal with that.
Right, but again, this is, at the moment we are not targeting that. So let me also here divide the question into two parts. And for the first part, actually, we have an expert over here, who's Jim. For analytical chemists, forensic sciences and whatnot, they do it a bit differently, in the sense that when they conduct their analysis, their instruments are connected to databases that tell them what it is that they're looking at. And there are situations in which what they're looking at is a substance which is known, in which case it can be matched with that. And there are other situations in which the substance is unknown. In that case, the situation is a bit more difficult to address, but it can be addressed. And that is kind of the second part of your questions, when you can look at novel chemicals, for example, that people are trying to make, or precursors which are a bit different from those that were used originally and whatnot. As a matter of fact, with analytical techniques like that, you can push it even to the point where not only you identify the chemical, but by looking at the impurity, what people call the chemical fingerprint of the particular sample, you can actually reconduct the chemical to a specific production plant. So that the chemical has been made with certain precursors, or that the chemical has been made within that batch. And this is done, for example, when one wants to match an environmental sample found, let's say, at a site where chemical weapons were deployed with batches which were identified prior to that, or also to, again, look at chemicals that are found in depots and whatnot. Where did those chemicals come from? Where did they originate from? And so you can use those type of techniques. But in all those situations, really, the people that do that don't really need a tool like ours, because they do have the means of telling what it is that they're looking at. And so this tool instead is intended to address a situation like, let's say there is an actor that wants to build wants to synthesize chemical weapons, orders some precursors,
Right.
From a supplier that does supply chemicals, and the supplier does ship the chemical, perhaps without a license, perhaps because they haven't even realized that they need a license for that. Or if we're looking at something that is done intentionally, one could even, a supplier that wants to supply a chemical to an actor can certainly provide a name which is different from one of the control names, or an actor can seek a variant of the chemical that has a different cache registry numbers and things like that. And those are all situations which an export control officer today would not catch. But again, this is not for intended for those who are trying to catch those who are trying to smuggle chemicals by declaring something else. It is intended to catch declared transfer of chemicals that are that wouldn't be catched in a straightforward manner just by matching names and cache registry numbers. It is also intended to allow for a more comprehensive, that in fact this was my first idea, a more comprehensive way of crafting these lists. Because I showed you that some of the entries are families of chemicals, but many others are individual chemicals. And lists that are directly targeted towards export control officers or customs officials, like the WCO list, they only have individual chemicals. And so that means that for G agents, they only have 2 or 3 that are listed. So G agents are those that belong to the agents like Sarin or Soman, those that were synthesized in Germany prior and during World War II. So that's not great, right? Because if you make a control list that is like that, clearly there are many more agents than the examples that you can list. There are many more precursors than the example that you can list. And you can always, as you were suggesting before, come up with a different chemical which looks a little bit like what has been done before, but it's a bit different. And that's exactly the goal of having families in there, right? That first entry that I showed, right, that has more than 100,000 chemicals in it. And so why don't people use families more widely? Because they're difficult to interpret, as I told you, right? So for an export control officer, it's almost impossible to do that. But if we build a tool like this, and a tool like this gets adopted, then families of chemicals can be used much more widely in these control lists. And therefore the control list will become more comprehensive, stronger, and we will have more controls on what gets transferred.
Excellent. I mean, and I kind of agree with you. I understand the chemical structures a lot more from the families, not being trained as a chemist, but being a geometer. I immediately looked at the structure and I saw, for example, that staircase. I saw one time it was rotated, and I could see how you would want to allow up to certain morphisms of space to be able to identify the chemical. And I think that's a very, very strong way to start looking at classification. So, but the bad actors seem like they've got it's going to be kind of so hard to catch them that maybe your tool could catch people who are shipping things, honestly. We can possibly identify that these things could be ingredients, but then, if it's shipped covertly, that's going to be a real problem. And that's where, back to John's question, is there some kind of spectral analysis, hyperspectral analysis that people like into the signal processing community can help with the problem? So,
and that gets into Jim's domain.
Right?
And the answer to that is yes.
Yeah.
I just reviewed a proposal from it's from Finland they're scared to death of all the Novichoks that might be.
Oh yeah.
Novichok isn't just one chemical. It's as Stefano will tell you, it's a family of things. And living on the border with Russia, one might be a little bit nervous about how spectrally how you identify what's coming at you.
Right.
Yeah.
Right.
Fascinating.
And in fact, with the Novichoks, one of the things that I've been following is that there is certainly a need to cover more thoroughly Novichoks by the Chemical Weapons Convention. We, Greg Koblenz from George Mason University and I have been following this issue. We had already pointed out when the Chemical Weapons Conventions were amended right after the 2018 Skripal incident to add some Novichoks in it. We have been following the thing prior to the amendment and after the amendment, and we already pointed out when the amendment was in the works that it was not comprehensive enough, that there were certain Novichoks that were left out. And in fact, then when the Navalny poisoning occurred, through the analysis that Jim was mentioning, it became clear that in fact the Novichok that was used to poison Navalny was not one of those that had been added to the CWC schedules with the amendment, but was a different one, right? The family that we were also arguing that should have been added. And I have a paper under review, Greg and I have a paper under review right now where we laid out the way that a further amendment should be crafted to cover the Novichoks that at least those that we know that have been made and through a family approach, and precursors for the synthesis as well.
Wow, fantastic. Do we have any other questions for our speaker?
I suppose. Yeah, I mean, my question is sort of ill-formed, but it's so as I understand, it's like you have a whole list of chemical names, and they're pretty hard to group together. Where'd you go, Stefano?
I'm right here.
Oh, there you are. Your window shifted. I'm talking there, and now you're back. And so it's really hard to tell what groups with what. So it's a division and classification problem. It's hard to tell from the names, but once you can put them into a structure, then you can start organizing them better.
Right.
And so it's a question of what would you want to do the reasoning from? And this seems like one of these problems that people in symbolic AI often deal with not just with chemicals, but with general structures. Like Mike Trainer works on these type of problems with social situations where the goal is to say, well, what's the format of the underlying structure that you can use to start making your connections from? Am I thinking this right, or am I thinking it for?
Let me show you something else.
No, that's.
Let me show you. Oops, no, I made a mistake. Let me show you something else that can perhaps help us answer the question. The main issue is not that it is difficult to group the chemicals together by structure. The main issue is that it is difficult to do so for those who don't understand chemistry well, right? And the tools allows them to do that. So for one thing that we've done, am I sharing the screen now?
Mm-hmm.
Yep. Yes, yeah.
So one thing that we have been doing, and this more to facilitate the communication between chemists and non-chemists that work on chemical security, is to actually have a curated version, curated and structurally annotated version of this CW control list, of these tables. So for instance, if you look at here, This is all on my website. I can actually give you a link to it. I can put it in the chat for those who want to look at it. So for instance, here, rather than having just the entry number, the definition, and the definition of the family name, we provide a picture, right? This is the structure, and so then, as you can see, the two examples. Let me make it a little bit smaller. The two examples underneath, when you look at the structures, you can see how they are related with one another. This is two variable groups over here, which here that are filled by, you know, different specific chemical groups, a methyl and an isopropyl over here. Here a methyl and the pinacolyl group that I was mentioning before. It's very difficult to communicate this to a non-chemist just by looking at the names. If you show them the structures, then how those chemicals are grouped becomes much clearer. If you look at the Novichoks, for instance, same thing. This is one of the families of Novichoks. They have here, as you can see, 4 variable groups. There can be, you know, a number of different chemical groups, and so this, when you match it, you will see that it matches the same structure. Visually, you can see, for example, how these two are related, right? This is essentially the same as this, except that this group over here is shorter than this one over here.
So for someone at the border, they don't necessarily need to know how they're related. They need to say, well, this is in some family that we have to get this stopped, or we have to label it, right? Because they're at the border, their job is to find the chemical name or the structure and say, is this, should I let it go through or should I not?
Right, but the fact is that they're not seeing the structure, right? That they're just provided with that's exactly the point. They're just provided with the name and or the cash registry number. So they're provided either with this or with that. And for a non-chemist, looking at the chemical structure, even if they were provided the chemical structure, is not very useful. However, and this, I think, gets to your point, the structural identifier does exactly what you were saying, meaning the structural identifier, which is this one over here, this has in it the code for this structure. And so if we manage to change things and require that whoever ships chemicals not only needs to provide the name, but needs to provide the structural identifier for the chemical as well, then the issue can be solved easily, because then at that point, the structures can be easily matched, and you can easily figure out whether the structure that you're looking at is a structure that falls within the scope of those that are controlled, whether as a family or individually. So that's exactly the point. And if you do have
Right. So
Yeah.
the name is, so the goal is to either get everyone to provide the structure,
Right.
or be able to go from whatever's labeled to the
to
structure.
the structure, exactly. That's
And then there's a part, because from the names, they're not going to be able to necessarily go there, and there could be
Correct.
new names, there could be synonyms. But once they get to the structure, then they can make the decision.
correct. That's exactly it. Yes.
Yeah.
That's exactly what the system that we have does. It's let me show you the slide that we had before. That's exactly how this works.
Right. So, I mean, are there programs that would go from those structures to tell, so it wouldn't rest on human judgment to look at the structure to make the decision? Where
No,
you could
well,
just look at it, which is what you're,
this is exactly what I was showing, right? I mean, with
yeah,
this,
that's right.
you can go from the name to the structure, and that's exactly the
Right.
no,
And
fine.
then the structure, from the structure to the decision.
And then from the structure, here is the thing, right?
There it is. Thank you. That's on that slide
Yeah.
10. Right.
Yeah.
So,
Here is the thing, yeah.
so the first part was the convert to structure,
Exactly.
And then there is the query. So the really nice thing would be a good human interface where they start with a thing over on the left where it says enter cast number,
Right.
and it goes through the query in one for at the border. It'd be great to be able to do that in one step, right?
Right.
Yeah.
Right.
Well, this essentially already does it in one step. You just need to go, through the right. You need to click on the right place, let's say, to perform that.
Right.
But it is
Right.
one step, though. It is
Right.
one step, though. It is one step.
Yeah.
It's just, essentially, let me show again. If you have like this registry number right over here,
Yeah.
you just take it from here, and you just take it from
Yeah.
there, and you go in here, and that gets converted directly into a structure. Once you have the structure,
Wow.
then you're good to go.
Right.
So that's exactly the point. And of course, as we said, you're totally right, Art, that this is now, you need to click first here, then, you need to open the menu. There are 2,000 options over here. You need to choose the right one. Clearly, for
Right.
for control officers, it would be good to have, one slot where you can put whatever you have, and it all occurs over there.
Right. So then it becomes an HCI, a human computer interface question.
Yeah.
Right.
Which is-
Right. That's exactly, the issue that one of the two limits that I was addressing. One is the interface, something that is more suitable for whoever works on the front line. Yeah.
Well, I think we need to
That's really good. Thank you.
first
Sure.
thank Stefano for an incredible talk again. And I'd like to emphasize a point that today's discussion, and you realize we've been talking now for 22 minutes on just the Q&A part. And I want to emphasize a point that we, the STEM scientists at American University, need to do more of this. I think the interaction between departments, like Art knows, I'm very involved in computer science. I teach a class which is both math and computer science for them, and I like to interact with the computer scientists, but I especially enjoy interacting with the other scientists around campus because, as I like to say, one of the hidden resources of American University is science. And I think today's dialogue is proof again that we need to spend time talking with each other, asking questions, having events like this. So, Stefano, thank you for a truly spectacular talk.
Thank you all. Good seeing you all.
Yes.